Design of a pipeline for a fixed-point multiplication using single electron tunneling technology. Abstract for high operating speed, low power consumption, and high integration density-based equipment, are financially indispensable in engineering, science, and technology in the present era. Single electron tunneling device, SED, is one such equipment by which all Boolean logic gates can be implemented. SEDs and linear tunnel gates, TLG, are capable of controlling the transport of only an electron through the tunneling junction. It is a single electron that is sufficient to store information in the SED in the atmosphere of 0 K. Power consumed in the single electron tunneling circuits is very low in comparison with CMOS circuits. The processing speed of TLG-based device will be nearly close to electronic speed. The single electron transistor, SET, and LTG attracts the researchers, scientists, or technologists to design and implement large-scale circuits for the sake of the consumption of ultra-low power and its small size. All the tunneling events for the case of a LTG-based circuit happen when only a single electron tunnels through the tunnel junction under the proper applied bias voltage and multiple input voltages. For implementing a fixed-point multiplication circuit, LTG would be a best candidate to fulfill the requirements of it. Ultra-low noise is generated during tunneling through the LTG-based circuit. Different logic gates, a D flip-flop, a full adder are implemented, and based on them, a pipeline for a fixed-point multiplication is presented at last. Keywords: electron tunneling, Coulomb blockade, pipeline, multiplication, linear threshold gate. 1 Coulomb blockade and single electron transistor. A tunnel junction in Fig. 1a comprises a thin insulating barrier between the two conducting electrodes. It is having a capacitance C and a resistance. The electrodes of the tunnel junction may be a superconducting or semiconducting. If they are of superconducting, electrons with one elementary charge, 1.602 times 10-19 C, carry the current. In the classical electrodynamics, current can't flow through the insulating barrier. But in the case of quantum mechanics, there must be a positive probability, i.e., more than zero, for an electron residing one side of the barrier to reach the other side of it when the proper bias or input voltages are supplied. If bias voltage is applied properly, there will be a current flow. Neglecting other effects, in accordance with first order approximation tunneling, current will be following in proportion to the applied bias voltage. In the case of electrical terms, a tunnel junction shown in Fig. 1a behaves as a resistor having a constant value depending on its barrier thickness. If two conductors are connected with an insulating layer between them, there will have not only a resistance but also a capacitance in the junction. In this context, the insulator acts as dielectric and two conducting plates with dielectric forms a capacitor in the tunnel junction. For the discrete nature of electric charge, current following through a tunnel junction is a series of events in which merely one electron will be able to pass or tunnel through the tunnel junction. If the single electron tunnels the junction, the tunnel capacitance is charged with an elementary charge. 1.602 times 10-19 C, building up a voltage V equals, where C equals junction capacitance. When the capacitance of the tunnel junction is ultra small, the voltage building up in the tunnel junction may be adequate to prevent another electron to pass through. The electrical current is suppressed as the bias voltage is lower than the voltage created in the tunnel junction and the resistance of the device will no longer remain constant. The increment of the differential resistance of the tunnel junction around zero bias is called the Coulomb blockade 3, 10, 13, 17. The principle of single electron technology 2, 3, 4, 9, 16 is developed on the basis of the single electron tunneling and Coulomb blockade. Single electron tunneling circuit seems to be a promising candidate for future VLSI circuits for its ultra-low power consumption, ultra-small size, reducing node capability and rich functionality. A set 4, 5 made up of two tunnel junctions shown in Fig. 1b, having their capacitances and resistances 1, 2 and 1, 2 respectively, shares only a common inland with a low capacitance. The electric potential of the island can be tuned in by a third electrode, called gate, and the gate is capacitively coupled, gate capacitance, to the island. An extra capacitance, 1 may intentionally be connected to the island for the purpose of manipulating the gate voltage, input. The drain, source, and gate voltages are marked by and respectively. For proper operations of set both of the resistances 1 and 2 are to be greater than equals H/225.8 kO and charging energy EC equals E2/2C where equals 1 plus 2 plus 1 has to be greater than thermal fluctuations, I.E, equals 22, the product of the Boltzmann constant, K, and the temperature, T in Kelvin. The Boltzmann constant value is 1.380649 times 10 to 23 Joule/Kelvin, or 1.380649 times 10 to 16 erg/Kelvin. 2 inverter. The inverter 3, 7, 8 depicted in Fig 2a, is made up of two sets connected in series. The same input voltage is directly coupled to the islands of the set 1 and set 2 through two capacitors 1 and 2 respectively. The island of each set has a size smaller than 10 nanometers of gold and their capacitances must be less than 10 to 17 F. The output terminal 0 is connected to the common channel of the two sets and to the ground via a capacitor. To put down charging effects. For the inverter, the parameters values chosen are, 1 equals 0, 2 equals 0.1 times, equals 9, 4 equals 110, 3 equals 12, 2 equals 12, 1 equals 110, 1 equals 12, 2 equals 12, 1 equals 174. And, 2 equals 174, R1 equals R2 equals 100 KO. For simulation purpose, the value of C is taken 1 AF. The operation of the inverter will be like this: the output 0 value will be high when the input voltage VEN is low and 0 value will be low when the input voltage is high. For achieving this target, we set the voltages, 1 equals 0, 2 equals 16 MV along with the tuning gate voltages, at present, VEN both for set 1 and set 2. Now if is low, the set 1 is in conduction mode and the set 2 is in Coulomb blockade. This effectively results the output to voltage. And causes the output voltage to be high. Coulomb blockade interferes the steady flow of current because whenever the high voltage, logic 1, is applied to the input, it causes to shift the induced charge on each of the islands of the two sets by a fraction of an electron charge and keeps the set 1 in Coulomb blockade and the set 2 in conducting mode. As a result, the output shifts from high to low. In this work we assume the Boolean logic inputs corresponding to the voltages like, logic 0 equals 0 volts and logic 1 equals 0.1 times. We assume, for simulation and other purposes, C equals 1 AF then logic 1 equals 0.1 times 1.602 times 10-191 times 10-18 equals 0.1 times 1.602 times 10-2 equals 16.02 times 10-3 equals 16.02.16 MV. 3 multiple input threshold logic gate. The multiple input threshold logic gate 5, 7, 8, 14 consists of a tunnel junction, 2 multiple inputs connected at points A and B. Each input voltage, for the upper side is connected to point B through the capacitor, and each input voltage, for the lower side is connected to point A through the capacitor. Bias voltage is also connected to point B through a capacitor. Point A is grounded through a capacitor 0. The capacitor of tunnel junction is. This multiple input threshold logic gate can also be defined as a junction capacitor, CJ, circuit. Using the junction capacitor circuit we will be able to implement the linear threshold gate, LTG, being presented by the signum function of g, x, expressed by equations 3 and 4. F, x, equals SG and g, x, equals 0. 0, 1. Equals 0. 3. G, x, equals, times, equals 1. Dash O, 4. Where R being the n Boolean inputs and R being the corresponding n integer weights. The linear threshold gate compares the weighted sum of the inputs, times, equals 1, with the threshold value O. If the value of the weighted sum is greater than the threshold or critical voltage value then the logic output of the LTG will be 1, otherwise it will be 0. The tunnel junction capacitance and the output capacitance 0 are considered the two basic circuit elements in a LTG. The input signal vector elements 1, 2, 3, are weighted by their respective vector element capacitances 1, 2, 3, and added to the voltage, across the tunnel junction. On the other hand, the input signal vector elements 1, 2, 3, are weighted by their respective vector element capacitances 1, 2, 3, are being subtracted from the voltage, across the junction. The critical voltage required to enable tunneling action, and it acts as the intrinsic threshold of the tunnel junction circuit. The bias voltage, connected to tunnel junction through the capacitance, is really being used to adjust the gate threshold to the desired value O. When a tunneling phenomenon happens though the tunnel junction an electron passes through the junction from A to B Fig 3. The threshold gate-based implementations of the Boolean logic gates have the same basic circuit topology for all we have to draw in the subsequent sections. The threshold gates consist of a bias capacitance, a tunnel junction having capacitance, and an output capacitance 0. The and OR gates contain two input capacitors. For both the AND gates, the two input capacitors are C1P equals C2P equals 0.5. For positively weighted inputs. On the other hand, for the NAND and NOR gates, two capacitors hold the values as C1N equals C2N equals 0.5. For negatively weighted inputs, every threshold gates is augmented with an inverter/buffer. The function of the inverter/buffer is to invert the input of a threshold gate. The logic function done by the buffered threshold gate is being the inverse of which is done by the threshold gate itself. For instance, a buffered gate implements the function. For the rest of our discussion, when we refer to a logic function such as n, we imply the logic function performed by the entire gate, i.e., threshold gate plus an output buffer. The parameters used for the implementations and simulations of different gates like N, OR, NAND N, NOR gates and other combinational or sequential circuits are given in Table 1.6,7. 8. Design of D flip-flop using logic gates. The flip-flop is a sequential circuit used for storing data from two stable states. A classical D flip-flop is consisting of 4 NAND gates and 1 inverter shown in Fig. 8a. There are two inputs D and clock, and two outputs Q and Q. The input-output relationship is shown in the truth table in Fig. 8b. Truth table. On the basis of the pattern of the D flip-flop drawn in Fig. 8a, we can easily implement a D flip-flop with the help of threshold logic gate-based NAND and a buffer/inverter shown in Fig 2a, or 2c. The same parameters used in the case of a NAND and an inverter will be used in the TLG-based D flip-flop. The output is provided with the positive edge trigger of the clock. The input and output signals of the D flip-flop shown in the Fig 9b through 9e are the D flip-flop input signal, clock signals, output of the Q and output of Q respectively. For the purpose of high-speed operation of addition, the use of carry propagation adder, CPA, 19 is needed. The CPA adds two binary numbers of 16 bits and produces an arithmetic sum depicted in Fig 11b. The carries generated in this case in successive digits are propagated from LSB end toward MSB end. The CPA can be created either by using ripple carry propagation or carry look-ahead technique. Here we have adopted the first case, i.e., ripple carry propagation. A figure of a CPA, an example of its calculation and the symbol of CPA are given in Fig. 11, A, B, and C, respectively. 11 Carry save adder. A separate high-speed addition technique will be required for adding three numbers at a time, and we define this technique as carry save adder, CSA, 19. In CSA the carries will not be allowed to propagate from low to high end, but instead they will be saved in a carry vector representing a number. In a general way, an n-bit CSA is specified like this: we assume that A, B and C are three n-bit numbers expressed as A equals, -1, -2, 10, B equals, -1, -2, 10, and C equals, -1, -2, 10. The CSA operations are performed bitwise simultaneously on a column of digits to generate two n-bit numbers as I, sum vector, equals, 0, -1, -2, 10, and carry vector C equals, comma, -1, 10, 0, noted that, the leading bit for the, of course, is a 0 and the tail bit for the carry vector C is a 0. Input-output relationship will be expressed by the equations given in 19 and 20 for I equals 0, 1, 2, and 1, where indicates exclusive or AND, indicates logical or operation. Now, after the addition of three binary numbers A, B and C, we obtain the arithmetic sum, equals A.B.C. AND is obtained by bitwise addition of two binary numbers. And carry, shown in Fig 12, C, i.e., equals, plus. The operation of CSA is presented in Fig 12, D, and its symbol is given in the Fig. 12, E. Fig. 12, A, sum, B, carry. C, bitwise sum, D, n-bit CSA and, E, symbol of CSA. 12 Design of a pipeline for a fixed point multiplication. The PCA and CSA discussed above will be used for implementing the pipeline stages for a fixed point multiplication unit 19. For the design purpose we consider an example of multiplication of two 8-bit integer numbers a and b and their product p equals a times b, where p is a 16-bit number. The fixed point multiplication can be treated as the sum of 8 different partial products depicted in the Fig. Point 13, where p equals a times b equals 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 plus 0, in this case times, plus. Arithmetic multiplication and addition operations. At first, we have found out the area/element numbers, switching delay, and switching energy consumption for the individual linear threshold gates, using the same methodology as adopted for the Boolean gates. Next, we have calculated the same parameters for more bigger and complex circuits and that are presented in Table 2. 14 Comparison of set and TLG. For a CMOS/TTL logic gate the time delay/processing delay for a gate like NAND, NOR, XOR is 12 ns20, on the contrary the time required for tunneling through a single electron transistor, set, is approximately 4 ns45. The XOR gate using conventional logic circuits needs 16 transistors, whereas this function can be implemented with just one set 1, 2, 4, 5, 10 i.e. number of nodes are reduced to 1 instead of 16. If the error probability is assumed to be 10 to 15 then the delay for the inverter will be 2.3025 ns and similarly the other delays for the other gates can be calculated as shown in Table 3. And it is clear that the TLG-based circuit must be faster than the set-based circuit when. 15 Conclusion. In this paper, first how an electron tunnels through a single electron transistor and an inverter is discussed. A generic linear threshold logic gate implementation from which we have derived a family of logic gates like N, NAND, or, NOR, XOR which are elaborately discussed. All the gates along with a full adder and a D flip-flop are implemented and are verified by means of simulation using Simon. The number of elements for logic gates, their delays, power consumed for them are also given in a tabular form. By dint of all these LTG gates and an inverter, a pipeline of complex circuit called pipeline for a fixed point multiplication having 4 stages, has been presented. It is an 8 by 8-bit multiplication pipeline producing 16-bit output. Among the 4 stages, stage 4 takes more time to execute with respect to other 3 stages. In single electron tunneling technology the logic gates are at least 3 times faster than CMOS-based logic gates. The atmosphere temperature should be close to 0 K in real operation.